So, as we saw, we had 3 questions which a phase diagram can answer, and we are now going to take up these questions one by one. The first question is, what are the phases present at a given point in the phase diagram? At a given composition, remember the x coordinate is composition and the y coordinate is temperature. So, at a given composition and temperature, what are the phases in equilibrium? This is a very important and a very direct question, and can be answered very simply by just looking at the phase diagram. So, remember, we come to our familiar binary copper nickel diagram. So, binary copper nickel diagram, we have been using, in fact, we have introduced only this phase diagram as yet. So, you are quite familiar with this now, binary copper nickel diagram, and we saw that this region is the liquid phase, this region is a solid solution phase which we call alpha, and this region is a 2 phase region. Then depending on where my constitution point is. So, for example, if I look at, let us say, this point. So, this point is, let me call this point A. So, point A, first of all, if I look at its x component, that is 60 weight percent nickel. So, this means it is an alloy of 60 weight percent nickel, and if I look at the y coordinate, it is 1200 degrees Celsius. So, a 60 weight percent nickel alloy, and I am only writing 60 weight percent nickel because we have binary alloy. So, this is the convention in binary alloy, since the other component obviously will be 100 minus the component which you have given. So, for example, 60 weight percent nickel automatically means that it is 40 weight percent copper. So, if you so wish, you can write, but giving one component, the proportion of one component is sufficient to define the composition for binary alloy. So, we have 40 weight percent copper. So, 60 weight percent nickel, 40 weight percent copper. Either of them you can give, but since we are saying that we are using weight percent nickel as our composition axis. So, we will give 60 weight percent nickel as the composition of this alloy. So, this is my point, and the alloy has been equilibrated at 1200 degrees Celsius. So, the question, what is the phase here? All you have to do is to see in which region it is falling. Since it is falling in the alpha region, we will say that this is an alpha phase. Phase is alpha phase. Now, let us look at another alloy. Just look at this one. Alloy B or constitution point B. So, if we now look at its x component, that is 50. So, the composition is 50 weight percent nickel. So, it is a 50-50 alloy, and if I look at the temperature, I find that it is 1250 degrees Celsius. So, an alloy of 50 weight percent nickel, 50 weight percent copper is being held at 1250 degrees Celsius. So, what are the phases present? So, this time we get a little bit more interesting answer, because now it is falling in the 2 phase region. So, we will find that 2 phases are present in this alloy. So, both alpha and liquid are present at this point. So, at this point, if I take such an alloy and heat it to 1250 degrees Celsius and hold it in equilibrium at that, means I wait for long enough time for equilibrium to be achieved, then I will find that alloy is a mixture of two phases. So, this is a two-phase structure. This is the basic function of a phase diagram, and this is something which phase diagram can very easily answer. You just have to look at plot the point of your interest on the phase diagram and read the phases present. An interesting thing which happens when you, so let me draw the boundaries. So, an interesting thing which happens when you look at a phase diagram, we have only looked at this phase diagram as yet, but you must notice that if I am that on the left hand side is the liquid phase, on the right hand side is alpha phase, and in between liquid plus alpha phase is there. This is not by accident, but this is always going to be true in a binary phase diagram. So, we write it as a rule. So, that is if I cross phase boundaries across a horizontal line such that at one end I have a given phase and at another end I have another single phase. At one end I have one single phase, that is what this one means, that I have a one single phase, in this case liquid. At another end I have another single phase alpha, then in between there has to be a region where mixture of these two phases should be present. So, liquid plus alpha. So, this is always true in a binary phase diagram, and we call this with a name 1-to-1 rule. Although this name is not very common in literature, but we will be using in this course. So, let me write this down. If we move horizontally, means since our y axis is temperature, moving horizontally is moving along an isotherm. So, if we are moving along an isotherm from one single phase in this case let us say example liquid to another single phase in this example alpha. So, this is for example, it can be any phase, example liquid, example alpha, then we will always have a two phase liquid plus alpha region, whatever the single phases were there. So, if one phase was alpha, another phase was beta, then the two phase alpha plus beta will be present. So, we will always have a two phase region in between. So, this is important, and in fact, many standard phase diagrams which you will come across in the literature, many times they will list only the single phase region, because the two phase regions always can be found as the combination of those two single phase regions. So, sometimes you will find in the phase diagram that the two phase regions are not labeled. So, this 1-to-1 rule is helpful from that point of view.